This is section 6.2, part 2, and we've been talking about finding the area between two curves. Our criteria for picking the horizontal versus the vertical rectangle has always been, which one can I draw a consistent representative rectangle for, so that it's always going between the same two curves. Sometimes, unfortunately, it's impossible to do that. And in those cases, it's impossible to find our integral or our area unless we use more than one integral. We can't do it with just a single integral. There's a variety of reasons this might happen. Here are a few examples. One possibility is it's possible that the graphs of the functions intersect within our desired boundaries. So for example, if I had one function here and another one there, then I've actually enclosed two distinct regions. And the problem here is going to be that thinking vertical rectangles, right? Top minus bottom on this side would be the black curve minus blue curve, but top minus bottom on this side would be blue minus black. So we'd have to set that up as two separate integrals. Another reason why we might need two integrals is sometimes it's just plain impossible to draw one single representative rectangle that applies to the entire region, no matter what we do, vertical or horizontal. I'm going to try and draw you a region like that. Maybe something like this. I've got three boundary functions here, and I'm trying to find the area of that region. Notice that vertical rectangles won't do it, because over here I'm between the curve and the positive sloped line, while over here I'd be between the curve and the negative sloped line. But horizontal rectangles won't do it either. Up here I'd be between the two lines. Down here I'd be between the curve and the line. So neither the horizontal nor the vertical rectangles will give me a consistent representative rectangle that works everywhere. Instead, I'd have to split that region up into two pieces and work with the two pieces as separate integrals. The third and final possibility is sometimes one of our functions inherently just requires the use of two integrals. The two most common situations here are piecewise functions and absolute value functions. Our next three examples will actually show us one of each of these, and we'll see how we can set up our two integrals in order to find our areas. So, in example 4, we are going to go ahead and set the integrals up by hand, and we're going to go ahead and evaluate them by the calculator. Right. As usual, we'll graph, we'll shade our region, and we'll draw our representative rectangles. So, for part A, we want the region, and actually this is a typo, that should be the region below the line. Y equals negative 4x plus 6, and also bounded by the graphs, f of x equals 2x squared, and g of x equals 4 times the square root of 2x. That's a little better. All right, so again, it's easiest to graph this probably on Desmos, although you can certainly do this on the calculator. I'm going to do a quick Desmos graph for us to help us visualize this. So my first line is y equals negative 4x plus 6. I've also got the parabola y equals 2x squared. And then finally I've got the square root curve, 4 times the square root of 2x. And although it graphed it, just to be consistent, I'm going to put y equals there as well. All right, so I can see this region in here. It's going to be my region for my function, or for my area rather, that I'm trying to find. It's below this line, and then it's also bounded by both the square root graph and the parabola. I'm going to go ahead and see if I can, maybe I can just move this out of the way a little bit here, and see if I can sketch that picture over here. Let's see. I'm not going to worry too much about getting things perfect as far as lining up my units or my sizes. I'm just going to get the general feel for this, and then I'll label the points. So here's my square root graph. Y equals 2x squared. Here's the square root graph here. Y equals 4 square root 2x. And then I've got the line kind of coming down like this. Y equals negative 4x plus 6. And I'm looking for this area. Okay. And again, I knew it was this one and not that one because we specifically said below the line. All right. Hopefully you can kind of see where my problem is. If I tried to use vertical rectangles, I would be fine here. I'd be between the black and the pink curves. But when I get over here, I'd be between the black and the blue. So vertical rectangles won't be consistent. Unfortunately, neither will horizontal. Over here, I'd go pink to blue. Down here, I'd go pink to black. So I'm going to have to do two integrals. In order to do this, let's go ahead and get the intersection points. That one is 0.5, comma 4. I'm just going to label them on here. And this one is 1, 2. And again, you'll notice that I didn't spend a lot of time trying to get this to line up perfectly with my grid. I'm just labeling the points and accepting them for what they are. All right, I think that's everything we need from Desmos. So let's go ahead and get rid of that. And since everything's already solved for y, and I'm going to have to use two integrals no matter what, I'm going to go ahead and leave these as vertical rectangles so that I don't have to go back and solve for x. So I'm going to split my region right here along the line x equals 0.5 along that vertical line. And I'm going to do one integral that's going to represent the left side and another one that's going to represent the right side. I'm going to give it a different color just to help us see it. All right. The region on the left, it's this one. If I think about my representative rectangles, this diagram is getting a little bit cluttered, so I'm going to go ahead and do my work down here. The base would be a little piece in the x direction, so delta x. The height, I'm going to go top minus bottom. So the top is the square root curve, 4 square root 2x, minus the bottom, which is the parabola, 2x squared. So the area of my rectangle, base times height, delta x, times 4 square root 2x, minus 2x squared. The total area, I'm going to integrate in order to sum up all the areas of the little rectangles. For square root 2x minus 2x squared, the delta x becomes dx. And then let's see, my limits of integration. I need x values, so I'm going to start here at x equals 0, and then I'm going to stop when I get to that dotted line at x equals 0.5. And that'll define that first region, the one over there on the left, which I've got shaded in yellow. All right, I pre-did this integral in my calculator, and I actually got 5/4 when I did it. Just plugged it in the calculator like we've been doing. Let's now do the one over on the right. I'm going to think about a little representative rectangle over here. And again, just to help me not clutter my diagram too badly, I'll label over here. My base is once again a little piece in the x direction, so delta x. And again, height for a vertical rectangle, always top minus bottom. The top this time is on the line, negative 4x plus 6. Subtract the bottom of the rectangle is on that black one, the parabola, 2x squared. So the area of the rectangle, base times height, looks like this. That's for one little rectangle. I need to sum up the areas of all of them, which I know I can do by using an integral. Again, my delta x becomes dx. And the x values here would start on the dotted line, which is x equals 0.5. And I'm going to stop when I get to this intersection point, which has an x value of 1. Again, I just went ahead and put that in my calculator, and I got 11/12. And again, that was just a little piece over there on the right side that I had shaded in orange. Okay, the final answer then, the area of the entire region is just going to be the sum of these two. And that comes out to 13/6 if you add it either by hand or on a calculator. All right, so there's one example. This was just a region that didn't work with one integral. No matter what I did, I couldn't get either horizontal or vertical rectangles to work consistently through the whole region. Let's try this one next. This time I want the area bounded by y equals x squared minus 2 and x equals the absolute value of y. As soon as I see that absolute value, I know that I'm very likely to need two separate integrals. I'm going to go ahead again and just pull up Desmos for us so we can graph this. And let's see here. Our first function was y equals x squared minus 2. So I've got that parabola. And then my second function was x equals the absolute value of y. Over here to functions. Oh, actually, absolute value is right here. And you can see, if I make this just a little bit bigger, let's see, I need to go down a little bit farther, so let me change the y-axis to maybe -8 or something. There we go. You can see it pretty well now. All right. I'm going to try sketching that on my graph. So I've got my parabola, and again, I'm just going to label things. I'm not going to worry too much about getting things in the exact right spot. There is y equals x squared minus 2. And then there is x equals the absolute value of y. And we can see that the region that's enclosed by those graphs is this one right here. Okay, in this case, my problem is that the absolute value function, even though I'm consistently going left to right from the absolute value function to the parabola, the absolute value function is not one that we know how to integrate. What we're going to have to do instead is consider it in its individual pieces. Before I leave this, let's just verify that intersection point is 2, 2. And this intersection point is 1, negative 1. All right. So, because I can't put the absolute value in an integral, we have no formula for integrating the absolute value, what I'm going to do instead is I'm going to go ahead and think of this as its two pieces. This one, let's see, would actually be x equals y. Well, this one would be x equals minus y. Right, this one has the positive slope. That one's got the negative slope. And so I'm going to have to think of them as two separate functions, like a piecewise function. When I do that, I can still choose to draw my rectangles horizontally, and that's going to be fine. But I will have to break it up right here, because this one will go from the x equals y to the parabola, and this one will go from x equals minus y to the parabola. So I'll do the bottom separate from the top. All right, let's do the top section first. Since I am choosing to do horizontal rectangles, I know I need the x equals form. So I'm going to have to solve this equation for x. X squared would equal y plus 2, and that means that x would be the square root of y plus 2. Now again, technically, that should be a plus or minus square root, but notice that everything here is on the positive x side, so I chose the positive square root. Okay. So instead of this and this, I'm going to use that as the equation of the parabola, or the piece of the parabola. All right, on the top, this is the part that we have shaded in yellow. The base of that rectangle is a little piece in the y direction, so I'll call it delta y. And the height is actually the length of the rectangle, so I'm going to go right minus left. Right is the parabola, square root of y plus 2. Minus left is this line, where x equals y. So the area of my rectangle, base times height, square root y plus 2 minus y times delta y. And when I add up all the little rectangles, I actually end up getting an integral. Okay. That top section, I need y values. So starting here would be a y of 0, and ending up here would be a y of 2. Okay. Again, I just went ahead and integrated that on a calculator. I ended up not getting a real nice fraction answer or anything. I got about 1.448. All right, what about the bottom section? Down here. Once again, the base of the rectangle is this little short piece. It's in the y direction, so delta y. And for height, I'll go right minus left again. The right side is still on the parabola, square root of y plus 2, minus the left side, which is on the pink line, where x equals minus y. So the area of a rectangle, base times height, would be square root of y plus 2, minus a negative will be plus y, times delta y. And adding up or integrating to get the full area, all the little rectangles, we have the integral of the square root of y plus 2 plus y dy. And my y values, the bottom one is -1. To the top, this section stops at y equals 0. All right, and when I did that one, calculator integral gave me 0.719. Total area? Adding these up gave me 2.167. All right, one last example. This time, I want the area between the curves y equals x squared and x equals 2 sine squared y. And this is actually just a graph like generated on Desmos. I've gone ahead and graphed it for us this time since the graph's a little more challenging to draw. But we are going to need some intersection points. So let me pull up Desmos so we can get those. If I've got y equals x squared for my first graph, and x equals 2 times sine y squared for my second, you can see the two pieces that we're talking about here and here. That intersection point, oops, a little too far, is 0.84, comma 0.705. And then this intersection point is 1.456, comma 2.12. All right, that gives us everything we need. And definitely this one looks like we're going to want to go horizontally again. Vertically would be awful. Notice that not only am I going to have to do two separate integrals for the two separate regions, but if I went vertically, this region over here would require two separate integrals just in and of itself. So definitely want to go horizontal on this one. I'm going to go ahead and we'll say this is our bottom region, and this is our top one. And I'm going to go ahead and do the bottom one first this time, I guess. So we're going to go horizontal. There's my representative rectangle. And before I go any further, I'm going to notice that this one is already solved for x, so that's great. This one, however, is not. So let's do that. Instead of y equals x squared, I'm going to go with x equals the square root of y. Again, technically that's a plus or minus, but I'm only in the positive x values. I'm in the first quadrant, so I took the positive square root. All right, my base is going to be the little piece. It's in the y direction, so that would be a delta y. Height, right minus left. Right is on the black piece, that's the parabola, so x would be the square root of y. Minus the left on the red curve, that's the 2 sine squared y. So the area of the little rectangle would be base times height like so. To get the complete area of the region, adding up all those little rectangles that I would have in here is really doing the integral. And these are y values that I need. So the limits of integration, I'm going to start down here where y is 0, and this ends at the intersection point where y is 0.705. And when I plugged that one in my calculator, I think I did it. Oh, no, I did not. Let's do it together. We're integrating from 0 to 0.705. And we've got the square root of, we'll have to put in x, minus 2 times the sine of x squared dx. And I'm getting about 0.183. By the way, double check. I should have checked first, but I think I'm in radian mode. I am. Anytime you have trig functions, you want to make sure you're in radian mode. All right, what about the top? This larger piece up here. Again, if I were to sketch in a horizontal representative rectangle, for that top section, my base is still going to be a delta y, little piece in the y direction. And the height, with horizontal always right minus left. And this time, notice they're just the reverse. The right side is on the sine curve, 2 sine squared y, minus the left side is on the x equals the square root of y. So the area of that little rectangle, base times height, will look like that. When I integrate to add up all of the little rectangles, delta y becomes infinitesimally small, dy. And my limits of integration still y values, notice. This starts when the y value is 0.705, and it ends up here when the y value is 2.12. So once again, thank goodness for calculators. This would be a pain to do by hand. And this time I get about 0.691 if I'm rounding to 3 decimal places. So total area, I'll just add my two pieces together. And I get 0.874. All right, that brings us to the end of section 6.2. I know we've done kind of a lot of examples here. This is really setting the stage for a lot of what we're going to do in the next several sections, and it's also setting the stage for some things that we're going to do in Calc 3. So this is a section to get really, really solid on. Make sure you have a good understanding of when and why you should use horizontal versus vertical rectangles. Make sure you have a good understanding of the bases and the heights of those representative rectangles, and then how they come into play. Do feel free to use technology, either Desmos if you've got access, or your calculator if not. And you can use the technology both to locate graphs and intersection points and stuff like that, and you can also use it to do the final integrals. Believe me, we're going to have plenty of opportunities this semester to do integration by hand. The integrals that we're doing so far, feel free to use technology. All right, so that's the end of 6.2.